Okay, let us start the course proper, so to say. And we start with introduction to Cartesian tensors. So Cartesian tensors obviously are not. It's a mathematical tool. It's not really part of the mechanics that we are going to learn in this course. But the language of Cartesian tensors is very important to us because it allows us to write the equations that we are going to learn in a very compact and mature fashion. So that's why we are going to learn it. First, some conventions. Scalar quantities will be denoted by Greek and Roman fonts, small case. Vectors will be denoted by small case bold. And we will also define quantities called second order tensors, third order tensors, and higher order tensors. Second order tensors, which we will deal with the most, will be denoted by capital bold. Third order tensors, we don't encounter that much in this course, and they will be denoted by these fancy, whenever we encounter them, if we encounter them at all, they will be denoted by these fancy capital letters. And this is known as a blackboard font. We will be dealing with fourth order tensors quite a bit, so they will be denoted by this blackboard font in capitals ABC. I might forget to remind you every time what is what, so I would urge you to remember this. So let me start with with vectors, which you know well, I suppose. Uh, we will make a few changes which may look a little cosmetic at this moment, but these are changes that are going to be very useful for us. So we are going to talk about a fixed Cartesian basis, and instead of calling it x, y, z axis, we will call x1, x2, x3 axis. It's a right-handed coordinate system, x1, x2, x3, and instead of calling the base vectors I, j, k, we are going to call them e1, e2, and e3. These are fixed vectors, and they are not changing with time. Their components are 1, 0, 0, 0, 1, 0, and 0, 0, 1, as you know. Then any vector u can be represented in terms of its components u1, u2, u3 as u1, e1 plus u2, e2 plus u3, e3. You know this. So we are not denoting the components of u as ux, uy, uz. We are denoting it as u1, u2, u3, just like we are denoting the coordinates of a point with x1, x2, x3 and not x, y, z. That's the only difference. You probably know these identities for vectors. You know that vectors, it doesn't matter if the order in which you add vectors. It doesn't matter, the addition of vectors is associative. So you can add u plus v and add w later, or you can add first v plus w and add u later. You get to the same answer as long as you use the parallelogram law correctly. And then for every u, there's a minus u that you can define, so that the addition of these two is a null vector. So these are obvious properties that you already know. Now, there are two kinds of products of vectors, dot products and cross products. So you probably already know those. So we will try to write the dot product and cross product in a slightly different manner than we have done before. So let us recapitulate the inner product or dot product of two vectors. You all know that the inner product of two vectors gives you a scalar. So u dot v gives you magnitude of u plus magnitude of v times cos theta, where cos theta is the angle between u and v. You also probably know that u dot v and v dot u are the same. The order of in which you take the dot product does not matter. If you dot u with 0, you get a scalar 0, and it is also associative. So u dot alpha v plus beta w, this is same as alpha u dot v plus beta u dot w. So uh, when u dot u is equal to 0, it implies that u equal to 0. There's no other way. And also magnitude of u, we will often write it as u dot u to the power half. And you can convince yourself, I think you are convinced already, that u dot u to the power half is indeed u1 square plus u2 square plus u3 square, to the power half, which is the magnitude of u. So the magnitude of u can be calculated by u, dotting u with itself and raising it to the power half. For a unit vector, the magnitude is obviously equal to 1. We also know that very well. Now, let me change gears a little bit and define a new quantity. And at this point, this quantity is just a definition. So this quantity is called the Kronecker delta. It's going to be our friend for a while. And we define it as an array of numbers right now. And the array of numbers follows this rule. So we call it delta ij. It has two legs, I and j, which is just an index at the moment, and I and j both go from 1 to 3. So they can take values of 1 to 3. So there are 9 values of delta ij that I can think of, and those are delta 1 1, delta 1 2, delta 1 3, 2 1, 2 2, 2 3, and so on. The rule that I have made, and this sounds very arbitrary right now, the rule that I have made for delta ij is the following: that delta ij, if I is equal to j, will be equal to 1, and if I is not equal to j, will be equal to 0. So this array of 9 numbers is actually an array of ones and zeros, where delta 1 1, delta 2 2, and delta 3 3, where I is equal to j, are equal to 1, and all other deltas where I is not equal to j are equal to 0. So this is the definition of what is known as the Kronecker delta. Now, immediately we see that the Kronecker delta has one use, and that use is that if I take any two basis vectors, I can write their dot product as delta ij. So if I take ei dot ej, I can write it as delta ij, because that is how the definition is. If ei, I and j are the same, the left hand side is equal to 1. That is equal to delta, say 1 1, 2 2, 3 3. So those are 1. Obviously it's valid for I equal to j. If I not equal to j, say I take the dot product of E1 with E2, then I get 0, because E1 and E2 are perpendicular to each other, and then this is delta 1 2, and delta 1 2 is also equal to 0. Okay, so this obviously is correct. This is an identity that we are going to use, and the identity is that if you dot the ith base vector with the jth base vector, you get always delta ij. So remember the definition of the Kronecker delta. Delta ij is equal to 1 if I equal to j, is equal to 0 if I not equal to j. And also remember the fact that the delta ij represents the dot product between two base vectors of the Cartesian system, ei and ej. Okay, so let's move on. Okay, the summation convention. So consider a set of linear simultaneous equations. Let's start with this. So I have a quantity y1 and a quantity y2, which is given as a linear combination of two other quantities, x1 and x2, in this fashion. a11, a12, a21, a22 are coefficients that that are known to us. So we can write this equation in a slightly shorthand manner by replacing this 1 and 2 by k, with the understanding that k can take values equal to 1 or 2. So we can write these two equations as one equation, as yk equal to ak1 plus ak2. So if you put k equal to 1, you get the first equation. If you get k equal to 2, you get the second equation. So it can be written like this, with the understanding that k goes from 1 to 2. We can write it even shorter. So we can say yk is equal to I going from 1 to 2, a ki xi. So this is a summation symbol, and it shows that now you have to sum over I from 1 to 2. So when you put k equal to 1, you get the first equation, and then you sum over I 1 to 2. So you get 1 1 x1 plus 1 2 x2. So that's that's how you have shortened this two equations into this one uh, summation equation, which is much more compact than what you had here. Actually, we can even get rid of the summation symbol if we adopt what is known as a summation convention. So the summation convention says that uh, if you have an index that is repeated, so these are called indices. If you have an index that is repeated in an expression, so in this expression you have an index I which appears twice. If you have an index that is repeated, then an invisible summation symbol is to be assumed here, and the context will tell you uh, what are the limits of the summation. So in our case, the context tells us that I is a summation is a index that is repeated, and the summation goes from 1 to 2. It can be 1 to 2, 1 to 3, 1 to n, whatever you like, but the context has to make it clear. So the basic understanding is that the summation convention says that whenever you have a repeated index, you have a invisible summation symbol in the front of the expression. So this is the repeated index, and then you have another index that is there present on both sides of the equality sign, and it's called a free index. So k in our case is the free index, I is the repeated index, and therefore on I we have an invisible summation, and in this case the context tells us that the summation goes from 1 to 2. Now uh, one fact that is important about repeated indices is that it does not really matter what we use. Here we have used a repeated index called I. I could have used a repeated index called M. So I can change the repeated index on the right of the equation without changing the meaning of this equation. If I change it to M, it's still a repeated index, and still there is an invisible summation on M at the front. But if I want to change the free index on the right, I will have to change it on the left as well. So if I change this free index k to a free index n, then we will have to change it on the left hand side as well. If we change it on the right, we will have to change it on the left. So that is the basic difference between the repeated index and the free index. A repeated index denotes a summation, an invisible summation over 1 to 2, 1 to 3, or whatever the context demands. And a free index does not denote a summation, so we can change the repeated index to any symbol without changing the meaning of the expression on the right hand side of the equation, but we cannot do so for the free index. The other thing that you should remember is that a repeated index cannot appear in an expression more than twice. So twice means there's a repetition, there's a summation, there's an invisible summation that has to be done. But if it appears more than twice, then it becomes confusing. So whenever you have, when you learn tensors more and indicial notation more, whenever you get a repeated index 3 times, you know that you have made a mistake somewhere. So remember that repeated indices can never occur more than 2 times in an expression. Let us do a small problem. Uh, this is just a use of the summation convention. So I have two equations. One is y given in terms of x's and x given in terms of z. So what we will have to do is we will have to express y in terms of z. We have to eliminate x from these two equations, and of course by now you understand that yi equal to aijxj actually hides 3 equations, each with 3 terms. So I am in this case assuming that I and j go from 1 to 3. So the first equation is y1 equal to a ijxj, and since j is a repeated index, there's an invisible summation over j. So the right hand side is actually a11x1 plus a12x2 plus a13x3. So y1 is equal to a11x1 plus 12x2 plus 13x3. Similarly, x1 is equal to b11z1 plus b12z2 plus b13z3. So this is a set of three simultaneous equations, each with three terms connecting x1, x2, x3 to z1, z2, z3. Similarly, this is another simultaneous equation which connects the three components y1, y2, y3 to the three components x1, x2, x3 of x to these coefficients which are a11, a12, etc. Now you will have to eliminate x and find the relation between y and z. The way we do it is, let's take the first equation. Let's take the first equation and write it in this manner. Remember, we can change this repeated index j to anything we want. So we change it to m. And the free index, we change it to n on both sides. We have to change on both sides. So yn is equal to a nm xm. We could have also written it as yi equal to aim xm. That would have made absolute sense and the same sense as this. Similarly, we write xm as bmpzp. Again, p is a repeated index. We can put whatever we like, and we put m here. So we have to put m here as well. M is a free index. Now, why did we use xm here? Because we have xm here. We have used xm here, and we want to replace this xm, with this expression, and that's what we have done. So we have yn equal to anm bmp zp. Now there are two repeated indices here. Sorry, we have two repeated indices here. M, there's a summation over m here. There's a summation over p here. So there are two summations here. 1 over m going from 1 to 3, p going from 1 to 3, and there's one free index n that appears on both sides. So you can change it to yi equal to aim bmp zp. You can change it to yi equal to aik bkl zl. That's also possible. So the repeated indices can take any value that you want to give them, except that they should not appear more than 2 times in an expression. Now you can open up this expression. So you can again see that n can take values from 1 to 3. So this actually is a set of 3 equations. And each equation has a summation over m and a summation over p. So each equation will have 9 terms in it. So it will have 9 terms in it, and the 9 terms are grouped in threes because zp can take 3 values, z1, z2, z3. So these are the new coefficients. These are the new coefficients. A, N, M, B, and P are the new coefficients that now relate y to z. And we have got that just by the use of the summation convention.